Let's talk about torque, about what it is, and about how to find it quickly. Remember the map of core models, and look here over on the right. These are the models for rotation, and those models involve torque as the agent of change. So the torque can either change the dynamics, it can be the torque is I alpha, or it can be that the torque, the sum of the external torques, changes the angular momentum of a system. Either way, the torque is the angular agent of change. Now, you have a good deal of intuition about torque because you've had to pull open a sticky door, or maybe you've had to try to tighten or untighten a nut with a wrench. So let's consider that second example, that there's a nut here, and you want to twist that nut with the wrench. Well, if you pull on the end of the wrench with the force as shown there, not much is going to happen in terms of rotation. Maybe you'll pull the wrench off the nut, but you won't rotate it. In fact, with the force aligned perfectly, the system doesn't have a tendency to rotate either way or the other. Well, let's try a different way. What if we put the force perpendicular to the wrench? Well, this is obviously going to turn the wrench and the nut around in the clockwise direction. So this is going to provide quite a bit of torque. What if we took an intermediate case and we pulled the pulled the force at some angle theta here with respect to the axis of the wrench? Well, that would be somewhat effective at turning this thing to the clockwise direction, but it wouldn't be totally effective. And so you can see that of these three alternatives, the number one here is the best. Now, is there a way to twist it even tighter, to put more torque on it with the same amount of force? Well, yes, there is if you have an extension bar. If you have an extension bar and you pull with the force perpendicular to the extension bar at the end, then that's going to give a considerable amount more twist or more torque than the case number one here. So this case here is the best. And what we've learned is now two things: that to get lots of torque, we want first to have the force be perpendicular to the wrench, and second, we want the force to act not at the point where we want to turn about, but as far as possible from it, so that we get the most leverage. Now I'm going to present a definition of torque, which is shown here, and it's going to be motivated by what we just saw. So in other words, it's going to be intuitively okay. So here's the idea of the amount of twist, or the amount of torque. In the first place, we're talking about the torque around a particular point, which is N here, where the nut is, the axis of the nut. Then the torque itself is proportional to the distance that the force is applied away from the nut, times the magnitude of the force, times the sine of the angle between the axis of the wrench, or the axis of the displacement vector, and the force itself. That assures that when the angle is zero, in other words, when you pull right along the axis of the wrench, that the torque will be zero, and it will be maximized when the angle there is 90 degrees. Now you'll notice one other thing about the expression that I've written here, and that is that it has a minus sign. The point of that is the following. When you have a two-dimensional problem, like the wrench here, and so the wrench and the plane of rotation and the force are all contained in the same plane, then there are two possibilities. One is that the torque is going around counterclockwise, and the other way that it's going around clockwise. One needs a convention for this, and you can pick the convention however you want, but I much prefer the standard convention, which is that positive is in the counterclockwise direction. And the reason for that is that we traditionally measure angles positively from the x-axis. Now, when we have that sign convention, then the force here is actually trying to pull the wrench in the clockwise direction, and therefore for the torque in this example we need a negative sign. If you really want a rigorous definition of the torque, then it's defined, and it's a three-dimensional definition, in terms of the cross product shown here of R cross F. and automatically you get the sign out of it, and also you get a direction. And if that direction is out of the screen or towards you from the screen, then that would be in the positive z direction, and that would be the positive conventional direction too, the way that I've taken it here. And so from now on, we're going to be using the top definition, though, this one here, because we're going to be working in two-dimensional systems, and we know, we can keep in the back of our mind, that is, that it's just the z component of the proper rigorous vector definition. Continuing this specialization to two-dimensional problems, and that's important and that's relevant and it's okay, because in introductory mechanics we'll almost always be working with a two-dimensional planar problem that can be written on a piece of paper or can be represented on the screen in front of you. Now for that case, the torque, as we just said, is in one dimension, it's in the z direction, and now what are the easy ways to find it? The answer is there are three basic methods. One is the tangential component of the force, the second one is the moment arm of the force, and the third one, the one we've been using, is the geometric plus the sign convention. So let's take a look at the tangential component. The idea of the tangential component, and now let's pick the force that is acting here as shown, and we're trying to find the torque about the point S here. Now, if we remember the discussion with the wrench, what's important is only this component here of the force. And that's the tangential component of the force. It's the one that is going around the circle like this. The other component, which is the radial component, is acting out here, but it doesn't give any contribution to the force. And so we can simply say that the torque about the point S is the tangential force times this distance r from S to where the force acts, to the point where the force acts P. And using the positive sign convention that we used before counterclockwise, then we get a plus sign here. We get the F times the sine of theta, that's the tangential force, and then it's multiplied by the magnitude of r. So that's way one, that's the tangential force, and it concerns taking very carefully and calculating out this tangential component of the force, and then just multiplying that as if it acted right here by the distance from the force to the origin. The second method that we're going to describe is the moment arm. And the idea of the moment arm is that we first think of what's called the line of force. We imagine that the force is, we think of it as acting along this line, and we can call this the line of force. And the point here is we want to take the perpendicular to that line, and this distance here is what's called r perpendicular, or the moment arm. And we can find that moment arm by looking at the angle here. This angle's theta 2, so the moment arm definition is just our moment arm is the distance that between where the force is applied and the center that we're interested in finding the torque about, this nut again, and it's times the sine of the angle, because it's the perpendicular distance from that line of force to the place we want to find the torque about, to N. Now then the torque is simply the moment arm times the force, and again we have to get the sign right, and we're using that the convention is counterclockwise positive, so in this case we get a minus sign there. So the torque is negative r perpendicular, or the moment arm, times the force, and if we look at that in some detail, of course, r perpendicular is r times sine, and so we get back to the original definition, which is r times f times the sine of the angle in between them. Now, the moment arm gives you insight into the following question: what if the torque, you want to find the torque about some point S, which is on the line of force. So let us say that we wanted to find the torque, but that the nut were up here. So we're now talking about the torque about point S? Well, any time that point S is on the line of force, then you can see quickly from this definition that there's no torque. And that's very valuable because in many cases, in many problems, you can pick S wherever you want, and if you pick it along the line of force, then there will be no torque. And that makes the problem computationally easier, and often it means that the angular momentum is constant, or the rotation speed is constant. The third easy way to calculate the torque is by the geometric way, which is actually the way that we use to first present the idea of torque. It's simply the radius, or the distance from R up to where the force acts, times the force itself, times the sine of the angle, and then in order to account for the convention on the sign, we have to put, in this case, a minus sign because it's for clockwise rotation. So in summary, the take-home lesson from this video is that when you're finding the torque, there are three easy ways: the tangential component, the moment arm, and the geometric plus the sign convention. But actually, you have to remember that the sign convention applies to everything. It applies to the moment arm and it applies to the tangential component. In both of these, you need a convention, usually counterclockwise is positive.